All right, today we're going to be talking about soils, and soils are a really important medium on our planet that allows plants to grow and many other organisms to grow. In addition, soils are a great place for us to transition our discussion about living organisms in the biosphere from before the midterm to the geosphere, which is the rocky, solid components of the Earth that we're going to focus on for the remainder of the semester. And that's because soils are a mixture of both organic matter, living organisms, and small rocky components in the soil. So, soil is a body of natural material that includes sediments. Sediments are small fragments of rocks that are loose and free to move across the landscape. Gases from the air, water, and organic matter. And when all four of these components are mixed together, they create this medium called soil that is capable of supporting plant life. So plants can't survive in water alone. Usually, there's some exceptions. Plants can't survive in just rocky material alone or organic material alone. They need a mixture of these things to be able to survive. In addition, we know that soils are created by primary succession. This is a process we also talked about before the midterm, and this is a process by which landscapes that have been scraped clean by disturbances all the way down to rock build new ecosystems as organisms move in and help break down the rock, and then the rock mixes with organic matter, with gases, and with water to create new soil. And so over time, landscapes can transition from positions, as we see on the left-hand side of the screen, where it's very rocky and barren, to landscapes that look more like the photograph on the right, which is the Central Valley of California, which has a rich and deep soil resource. So one of the really important things that soils do is that they provide nutrients to plants and other organisms. And nutrients are just simply compounds that are found in the environment, and organisms need these compounds to be able to survive. So there's two general categories of nutrients. There are macronutrients, and many macronutrients are organic in origin, so they come ultimately from living things. And what it means to be a macronutrient is that we need a macro dose of these nutrients, or plants need a macro-sized dose of these nutrients to be able to survive, or we need more of them. And these include things like carbon, nitrogen, and phosphorus. On the other hand, we talk about other nutrients as micronutrients, and many of these are derived from inorganic materials, so like the rocks and minerals that break down to create the sediments in soil. And these are just as essential. We can't survive without them, nor can plants, but they're micro because we need smaller quantities of these things to fulfill our requirements. So we get our nutrients from the food, but plants get nutrients from the soil. So without soil, plants might have carbon dioxide, they might have water, although mostly they get the water from the soil. They might have sunlight that we said are required for photosynthesis, but they actually still wouldn't be able to survive without these soil nutrients. So we want to go through and talk about these four components in a little bit more detail and talk about the roles that they play in the soil environment. And the first component that we listed was sediment, or these fragments of rock. Sometimes we refer to these as inorganic materials, or also parent materials. Parent materials are rocks that break down to form soil. And these materials often supply the micronutrients that we talked about, so the inorganic minerals and nutrients. And in addition, these materials can be important sources of water storage in the soil. So in this photograph on the left, you can see that this is a zoomed in picture of sand and silt particles, bigger size soil particles that are kind of shown in tan. The black fragments in here are organic matter, and then the green spaces are kind of the space between the soil particles, and those spaces contain water and air. So water can be stored in between those gaps in the soil. But when we look at the photograph on the right, we look at clay particles. Clay are the smallest size particles that make up soil. And the structure of these particles is kind of like an accordion or a fan, and these little tiny fans can expand out and can absorb water onto all the internal surfaces inside this fan. And so soils that contain clay are going to be really especially good at storing and holding water in the soil. So that's one important role that sediments play. On the other hand, the other component of solid material in the soil is made up of organic material. So this is decayed plant and animal material, or also decayed fungal, bacterial material, anything that comes from a living organism. Sometimes we call this material humus in the soil, not humus. This material tends to have a very dark color, and this material provides lots of nutrients in the soil. We mentioned that the macronutrients, things like carbon and nitrogen, are primarily derived from organic matter. And also, organic matter acts like a sponge and is really good at absorbing water, just like clay. So both clay and organic matter are good at holding water, much better at holding water than the larger size sediments, things like sand. A third component of soil is the air, or the gases, and these air pockets in the soil provide an important conduit through which these different kinds of life-providing gases can move. So oxygen is the most important one of those gases, and there are many organisms that live down below ground in the soil that need oxygen to live just like we do. So there's many kinds of animals. Here's a picture of a mole and an earthworm. Those are both animals. There's also many kinds of fungi and bacteria, and plant roots also need oxygen as well. When too much water gets into the soil, then there is not enough space for gases like oxygen to occupy and move around, and so organisms will come up to the surface of the soil because they're suffocating and they're gasping for air. And so when this happens, like right after it rains, you'll often see birds having a feeding frenzy on the surface of the soil as they're eating all these earthworms and other insects that are coming up to the surface trying to get a gasp of air. In addition, these air pockets in the soil allow for the removal of CO2. Plant roots create CO2, and other organisms breathe out CO2, and so we want to remove that from the soil and replace it with oxygen, and we need air pockets in the soil so the gases can move to be able to do that. Finally, soil water is really critical, and most people are aware of this because if you've ever had plants, you probably have watered them. And water is required for photosynthesis, as we've discussed before. But water is not only required for plants, it's also required by many other animals, or many other organisms, such as animals, fungi, and other microbes. And soil water is very important because water is an effective transport mechanism that helps move around nutrients and then sometimes undesirable toxins in the soil. So before we mentioned that water is really good at adhering to many different kinds of compounds, and so water grabs on to things like soil nutrients and moves them from the soil into plant roots, or moves them from the surface of the soil down deeper into the soil, and it's basically an important little transport mechanism to move these materials around. And a lot of the water that's below ground is referred to as groundwater, real creative name there. But actually not all water that's below ground is considered groundwater. Water that's up near the surface, that's bonded onto soil particles, where there's plenty of air pockets also in the soil, is not considered groundwater. But as we dig deep down below the surface, we'll eventually run into a zone where all the spaces that surround the solid particles are filled up with water. And that transition zone is called the water table. and then the water below that in the area of soil and fractured rock that is saturated with water, that's totally filled up with water, is called groundwater. Groundwater is a really important resource that we depend on in many parts of the world, and California is one place where we depend very heavily on groundwater. We access it by pumping water from wells. So if you drink water out of a well at your house, like I do at my house, you're drinking groundwater. And actually anyone who lives in Quincy drinks groundwater. That's what city water is here. And we also use lots of groundwater for agriculture, and it's a very important resource for us, which is an interesting topic. However, there's some complications about groundwater pumping, as so many people are trying to access water from below ground all at the same time. We're depleting this resource very quickly. So a lot of times people use the analogy like a milkshake, and if you have a milkshake and you stick a straw, which is kind of like a well, into the milkshake and you start sipping water out or sipping milkshake out, at first you might not draw down the milkshake very quickly, but all of a sudden if 50 people stick their straws in the milkshake and are all sipping, then that milkshake is going to disappear really quickly. And the many hundreds of thousands of wells that we have drilled across California are kind of acting like lots and lots of straws dipped into this milkshake resource or this groundwater resource. And one of the impacts that we see is that the ground is actually sinking as we're pumping water out of the ground. So the ground is collapsing in on itself as the water is being removed. And this process is called subsidence. So there's a famous photograph that was taken in the late 70s in the Central Valley area of California that's on the left hand of the screen, and it shows how the land level in the Central Valley has dropped from the 1920s to the 1950s to the 1970s. There's an adult man, we can imagine maybe he's close to 6 feet tall at the bottom of the picture, that gives you some perspective of just how much the land has sunk. And the land has continued to subside more since this photograph was taken several decades ago. So this is a pretty serious concern that people have. As the land collapses, it is creating problems for people, creates problems for things like foundations of homes and roads. It also depletes the ability for the soil to be recharged or refilled up with groundwater because the spaces that used to hold water have collapsed in on themselves. And also for certain people that live, for instance, around the Delta area in the Central Valley, as they are sinking, they might be finding themselves in a position that's below sea level. And so they might be vulnerable to encroachment from salt water, which is really detrimental to agricultural practices, to water practices, other things like that. On the right-hand side of the screen, there's a photograph, or there's an image that shows the subsidence that has occurred in an 8-month period between May 2014 and January 2015, which was kind of the peak of the drought a few years ago. And this shows that many parts of the Central Valley sunk more than 10 inches in less than a year, as so many people were turning to below ground sources to supply water. Another interesting problem that's related to groundwater pumping is that sometimes as we pump water off the ground, we can initiate these crazy phenomena that are called sinkholes. So sinkholes are created when we have certain kinds of geology or certain kinds of rocks underneath the ground, in particular when we have rocks like limestone that are relatively easily dissolved in the presence of water. So the water dissolves away the rock and creates these caverns or caves underground. And when these caves are filled up with water, the density of the water is strong enough to support the land on top. But as we drill wells down into the ground and pump water out of these spaces, Then air pockets are created, and air is not as dense as water. It doesn't have the same strength, and so the ground will collapse into these places that are created. And sometimes these are created by groundwater pumping, as I mentioned. Sometimes they're created by other natural processes, but they result is these really crazy phenomenon, these big sinkholes, and you can see on the left that there are photographs of these in all different places in the world, and they can really be quite big, and they happen very dramatically all of a sudden and can be really, really scary for people that get stuck in the wrong place at the wrong time. So the last thing that I want to discuss with you guys about soil is how soil forms. So we know that soil forms over time from a mixture of organic matter, sediments, water, and gases, but we want to think about the other kinds of things that influence the process and rate of soil formation. And there's a famous soil scientist who worked about 100 years ago in California, and his name was Hans Jenny. And he wrote this book called Factors of Soil Formation, a System of Quantitative Pedology, which is kind of a mouthful. But basically, this book laid out an equation for how soil forms. And he called this equation the state factor equation. The equation said that soil is a function of 5 criteria: climate, organisms, relief, which is also known as slope or topography, parent material, which are the rocks that make up soil, and time. And then he left these ellipses at the end of his equation to acknowledge that there's other things as well, but he considered these 5 things to be the most important criteria back in his time, and we today still consider these to be the most important criteria. So we're going to go through these 5 and think about them in more detail. So the first one is climate, and there are a lot of different components of climate, as we've discussed before this midterm, but 2 of the most important climate criteria that influence soil development are temperature and water. So as we've discussed before, warmer temperatures are conducive to faster rates of biochemical reactions. So photosynthesis is a biochemical reaction, but also all these kinds of decomposition processes that occur in the soil where organic matter is breaking down to make new nutrients and build new soil resources. These things are biochemical reactions as well, and they happen faster and soil gets built more quickly in environments that are warmer as opposed to colder. We generally said every time we increase the temperature by 10 degrees Celsius, we're going to double the rates of biochemical reactions. So that's a factor. And in addition, the water content on the landscape is also very important. So water is particularly important in its role in breaking down rocks to create the sediments that mix together with the organic matter to create new soil. And where there's water, the water is working hard to break down the rock. It's pounding against the rock, and in some cases it's dissolving the rock, and it's just facilitating the different kinds of chemical reactions that are breaking apart these big structures and creating small structures. So the photograph on the left shows a dry desert-like environment. There's a lot of rocks jutting out of the ground here, and that illustrates that the soil is pretty shallow. It's not very deep, and that's probably because this landscape is pretty dry. On the right-hand side, we can see a forest. We know forests grow in areas where there's more water available. And then if we go down below the forest floor, we can see this kind of deeper, richer soil resource that's facilitated by this wetter environment. The next factor is organisms, also sometimes called biota. And basically, organisms make soil. So sometimes simplistic organisms like lichens move into new areas of rock and help eat away at the soil. But there's all kinds of other organisms that live in soil and help build more soil over time. So biologists today actually think that there's more different kinds of organisms that live underground than above ground, but we often just don't appreciate this very much because we can't see these organisms as well since we live up above ground. But I have some photographs of different organisms here. On the far right, I have plants. We all know plants grow in soil, but you may not know that at least 50% of the biomass of the plant is usually going to be below ground. So these photographs of plant roots show you just how much is going on in the soil. Then at the top in the middle, there's a picture of a fungus that's growing in the soil. In the middle of the slide, there's a picture of a nematode, which is a small worm kind of animal in the soil. In the bottom in the middle, there's a little protist that is on top of a bunch of bar-shaped bacteria that are in the soil. And then on the left are two photographs of my favorite kind of organism, which are called tardigrades, also sometimes called water bears or moss piglets, which I just think are cute names. And these are these crazy creatures that live below ground in the soil and also above ground as well. But these are little kinds of animals that are eating things in the soil, pooping. So the third criteria is relief, which is the slope of the landscape or the topography of the landscape. And that's important because the slope position affects how quickly soil that develops will be eroding away from or accumulating on the landscape. And in this diagram, you can see that the blue below the trees that's supposed to represent soil is not the same depth everywhere, but it is accumulating more in places where it's flat, and then in places on the hill slope where new soil develops but then rolls away down the slope, the soil resource is much shallower. So the amount of soil that we're going to have in any given place is going to be influenced by its topographic or relief position. That parent material is another word to describe the rock that's breaking down to affect the soil. And this is important, first of all, because different kinds of rocks break down at different rates. They have different kinds of chemical structures, some of which are more vulnerable to breaking down in the presence of water and organisms and other things like that, and some of which are more sturdy. And in addition, different kinds of parent materials are made up of different chemical ingredients, and so as they break down, they have different kinds of nutrient content to support plant growth and other organisms in the soil. So in this diagram that I have here, there's a list of different minerals that make up rocks on the far left, and then right next to that you can see the chemical equations for these different minerals, and you can see that they're made up of different things. They have different ingredients in them. So soil that is made of a rock that had a bunch of muscovite in it might have plenty of K, potassium, Al, aluminum, Si, silicon, and O, oxygen, but it might be lacking in things like iron. On the other hand, a rock that has made up of lots of hornblende might create a soil that has plenty of Ca, calcium, and Fe, iron, but might be lacking in something like K, potassium. So the nutrient content of the soil is going to be influenced by the parent material. Finally, the fifth criterion in the equation is time, and that's because, like all things, the development of soil takes place over time. This image at the bottom of the slide here shows how after 100 years post-disturbance, you might have a very shallow amount of soil supporting some small vegetation, and then after thousands, tens of thousands, or hundreds of thousands of years, the rock will have mixed with organic matter to develop deeper and deeper and more complex soil resources. And in general, there's kind of a back of the envelope estimation that soil scientists use, which says that in areas that already have forests, so already have some soil and organisms there, it takes about 1,000 years to develop around 1 inch of soil. So in some places it might be a little bit less than that, only a centimeter. In some places it might be a couple inches, up to 10 centimeters of new soil. but that's a long time to try to build a new soil resource. And in areas that don't already have plants there, it could take a lot longer than that. So this all illustrates that soils are not really renewable resources. If we're losing soils on the landscape due to poor agricultural practices or poor construction practices, road building practices that are allowing large amounts of soil to be washed away, we're really damaging our ability to support ourselves with necessary plant growth in the future. And so having important considerations and responsible soil management is an incredibly important, even if it's not a glamorous thing that humans really need to consider to have a sustainable lifestyle on the landscape. So that concludes our discussion about soils, and please email me with any questions that you guys have. All right, have a nice afternoon.